To deliver a talk here. So I'm from the IIT BHU. BHU is actually, there is a very nice campus. Those who have not visited yet, for them I am showing this. Who have visited, they know the things. Anyway, so this is my title of my talk is the magnetic effect for that I show for the two-dimensional van der Waals system. And for those again, this IIT BHU, this BHU that is the founded by Mohammad Pandit Madan Mohan Malviya in 1916, and IIT BHU originated since 1919, and 2012 it became converted to IIT BHU.
Small comment.
Yes.
Madan Mohan Malviya's name is associated with it, but actually the inspiration and the suggestion came from Annie Besant.
Okay.
She was an Irish lady.
Okay.
Became president of Indian Congress.
Yes, yes. Her photo is also there.
By
Yes.
the British, and she, both Madan Mohan Malviya and Jiddu Krishnamurti were her disciples.
Okay, thank you, sir. So anyway, my group is working in different domains, from the 2D van der Waals to topological insulator, well semi-metal, Huisler alloys, and perovskite material. So today we will share some results on 2D van der Waals materials. So now what is the magnetocaloric effect that we have already, my topic is that magnetocaloric effect. When some magnetic material, that magnetic field is applied, what will happen because of the orderly orientation of the spins, the that heat that will be absorbed by the material, heat will be released by the material. As the heat will be released by the material, so the temperature that will increase. Now again, when the magnetic field is removed, because of the disorderness of the spins, that heat will be absorbed and the temperature will decrease. So this is the user, it is the environmentally friendly magnetic refrigeration technique. And this magnetocaloric effect actually it is the from the measurement of the magnetocaloric effect, one can detect the magnetic phase transition which arises due to the entropy variation due to the application of the magnetic field. So now that I will also, that is the magnetocaloric effect, we will discuss in the 2D van der Waals materials. So why the 2D materials, in the case of the low dimensional materials, exchange anisotropy and the strong thermal fluctuation, that is the effects on the spin lattice thermal degrees of freedom. The introduction of the 2D material, that is the van der Waals materials, it has the potential for understanding these effects because of the distinct properties of these materials compared to the bulk counterparts. And the 2D materials, why these are interesting, that is because of these reasons, and so finally there's a strong spin orbit and quantum effects, and also wide material variety and the low power feature devices. However, so first discovered the 2D material is as you know, that is the graphene, and graphene is a semi-metal and it has weak or no at all spin orbit coupling. And then another is the MOS2, that is it is having a strong spin orbit coupling, that is also very interesting material. And the other 2D materials are the black phosphorus and hexaboronitrate, which is insulator. Other than these, other important 2D materials are these, the CRI3, CR2, these are the hexagonal, and FEPS3, and these are the trigonal. In the posting already, Professor Zakir Hussain already mentioned about the MnBi2 Te4. So today we will discuss these two materials, FEPS3 and MnBi2 Te4. And FEPS3 actually, and also we have these both the material, that is FEPS3 and MnBi2 Te4, those both are the antiferromagnetic. Why we have chosen the antiferromagnetic? The reason is this is the actually, it has the no stray magnetic field and also ultrafast dynamics, and most importantly the thermodynamics of magnetism in this layered antiferromagnet, which is about FEPS3 and both the MnBi2 Te4. These are particularly the entropy changes, heat capacity anomaly, and the coupling between them is very important and interesting. So that's why we have chosen this two-dimensional antiferromagnetic material here to discuss. And that FEPS3, we have prepared the FEPS3 material by the CVT technique and chemical vapor transport technique, and this we prepared that the flakes, we got the flakes, and it is clearly the X-ray diffraction clearly shows the single crystal. And from the phase program we have seen that is the phosphorus atom that is it is coordinated with the iron atom coordinated with the 6 sulfur atom, and the sulfur atom again it is coordinated with the with the 3 phosphorus atom. So it is the interlayer coupling is via the SS interaction, which is very weak and easily exfoliated. And from the EDEX measurement and some same HRTM measurement, it shows that there is no impurity phases are there. So this is clearly saying this is these two-dimensional van der Waals is pure single crystal. So we have measured the magnetic measurement, the temperature variation as well as the magnetic field variation. With magnetic measurements we have done, and it shows that at around 119 Kelvin, at 119 Kelvin is the peak for both perpendicular to the AB plane and parallel to the AB plane. For both the cases we get that is the transition or peak maximum value at 119 Kelvin. That is the signature of the NIL, that is the antiferromagnetic transition. And this actually, the interesting thing is this, it is above the transition temperature that we don't find the exact paramagnetic phase. So this might be the characteristic of the low dimensional system, but with the spin-spin correlation, and from the DMDT versus T measurement we see that clearly at sharp peak at the T 119 Kelvin. Sorry. So the broader peak also we have mentioned that this is the characteristic of the low dimensional system. And one thing is this, the magnetization value for the perpendicular to the AB is larger than to the parallel to the AB. So it may suggest that the spin oriented along the C direction. And also from here, when for the M versus T curve, here you observe that when it is H perpendicular to AB, it is lower than the magnetization value is decreased sharply than the parallel to the AB. So that means in plane exchange interaction is larger than in the out of plane exchange interaction. And for the MH curve, you see, for when H perpendicular to AB, there is some the deviation from the linearity, and it suggests some existence of the ferromagnetic behavior that might be due to the canted antiferromagnetic state. And this is because actually this might be the reason that this might be due to the uncompensated spin at the surface or at the grain boundary. So therefore the perpendicular and parallel direction that the measurement it indicates there is a strong anisotropy in the FEPS3 system. We have also measured the heat capacity, and it shows that is again at the transition temperature, antiferromagnetic transition temperature is sharp peak, and when we apply the magnetic field, the peak decreases to shift towards the low temperature. This is again the indication of the existence of the antiferromagnetic phase. With application of the magnetic field, spin flops and it shifts towards the lower temperature. And we have fitted this curve with that is both for determining the electronic part and the phononic part, considering the Debye and Einstein model relation, and that we subtracted from this specific the heat capacity data, and we found that that is magnetic contribution in the specific heat here, and there is a sharp peak at the transition temperature 119 Kelvin. So it suggests that there is a collapse of the entropy when it is at the antiferromagnetic along with the when it is moving toward the antiferromagnetic state. This collapse might be due to the when it is moving to shift toward at the ordered state. What happens? The spin-spin correlation that may provide some spin lattice, that may provide a spin lattice interaction by decreasing the exchange restriction effect. So this is the reason that, so therefore from this measurement we may have that is the provide the macroscopic evidence that the antiferromagnetic transition in FEPS3 is accompanied by entropy driven modification of the lattice dynamics. And for this case, when we apply the magnetic field, it is observed that the entropy that is with the application of magnetic field, it is increasing. That increasing means, so therefore it suggests there is a magnetocaloric effect exists. So for that, what we have done, we have measured the magnetocaloric effect. Again, this is from here, you see, with the application of the magnetic field, with at different temperature, as the temperature vary, the value of the magnetization that changes again suggests that is the presence of the magnetocaloric effect. And for this, there is actually at the low temperature, it is at a particular temperature, that is the transition temperature, the maximum peak value is observed, and at the below the transition temperature, as you know, with the application of the magnetic field, spins will be oriented in an ordered direction. So that's why this value is decreasing. And for in this case, actually spin-spin correlation I have already mentioned that above the transition temperature, it is the paramagnetic state is not complete, the spin-spin correlation is still there, and because of that spin-spin correlation, that value is decreasing here. So therefore, and moreover, there is again, it shows the anisotropic behavior. In the delta Sm here, you see we are around 1, less than 1, and here it is 3. So this is the anisotropic behavior. It again supports the anisotropic behavior, the magnetocaloric effect. And from here we have measured the magnetic entropy change and the relative cooling power follow the power relations, and that is the delta S to the power n, and this n value that we observe 1.78 and 1.85 of different orientation, and for the antiferromagnetic case the value should be around 2, but for this case the value is slightly lower than the W2 that we have mentioned, that is it is the some canted antiferromagnetic states are there, so that's why it is deviating from the value of 2. And therefore now the form whatever we measure, that is the from the magnetocaloric effect, and that is the heat capacity, that is the magnetocaloric effect. It suggests the magnetocaloric effect in this FEPS3 system, it provides a thermodynamic probe of the lattice vibrations accompanied by magnetic ordering at the antiferromagnetic transition, so that it proves that is the not only the magnetic transition, but it proves that is the thermal lattice vibration in the antiferromagnetic state. We have also, we have already mentioned that it proves the lattice vibration, so we have measured the Raman effect, and it shows that is the Raman effect actually at the transition temperature around 119 Kelvin, there is some, that is the deviation from the linearity. And actually what happens, as I've mentioned, that is at the transition point from the specific heat, there is a collapse of the entropy. So this the release of entropy at Tn and the phonon frequency shift here, that is demonstrated that lattice vibrational modes are strongly influenced by the collapse of spin order. So therefore from the Raman effect measurement, we see there is a spin phonon coupling, strong spin phonon coupling is there. So therefore FEPS3 system, what we observe, that magnetocaloric effect, as we have mentioned, in this system captures the magnetic entropy change, but also provides a thermodynamic probe and also provides a thermodynamic probe to the lattice vibration accompanied by magnetic ordering at the antiferromagnetic transition. Already so many talks has already been done. So next we will discuss the MnBi2 T4 disposium of MnBi2. So many talks has been already discussed the topological insulators. I am not going to discuss those things, but I only say that when some magnetic impurity, because you know that in topological insulator at the surface state is conducting, at the bulk state is insulating, but and there is the Dirac cone is there, and this is the. But when there is some magnetic impurity is doped, or there is a heterostructure, that is the magnetic impurity and the topological insulator, a gap will open at the Dirac point, and and in that case time reversal symmetry will be broken, and this gap will open. Why this is important? Actually, that actually the Hall effect, that is the the topological Hall effect, that is this topological insulator, topological materials. For all those things, the main origin is the discovery of the Hall effect. This is very important discovery in the condensed matter physics. So this was discovered in 1879, and then quantum anomalous Hall effect, it was discovered after 100 years, 1980. Anomalous Hall effect, that was discovered in 1881, but the quantum anomalous Hall effect, it took 2013, almost more than 130 years. So this is important, quantum anomalous Hall effect, because you see in quantum anomalous Hall effect, without at zero magnetic field, you will get that is the Hall resistivity, or that is the Hall value of some finite Hall resistivity value would be there. So that is why it is important from the application point of view. Without application of the magnetic field, you will get the Hall resistivity. That is the quantum anomalous Hall effect. And what happens for the case of the magnetic topological insulator, the precise tuning of the Fermi level at the mass gap, that mass gap is observed because of the doping of the impurity, magnetic doping, or the heterostructure, that is because of the proximity effect. So in that case, what happened, by precise tuning of the Fermi level at the mass gap enables the observation of the quantum anomalous Hall effect. So you have to precisely tune the Fermi level, and in that is the gap, surface gap, that is induced due to the magnetic doping. So what we have done, so first it was discovered in the 2013 in that is chromium bismuth antimatter telluride system and vanadium bismuth antimatter telluride system. But the transition temperature was very low. It is 30 millikelvin. It was observed 30 millikelvin, but the transition temperature is around for this 30 Kelvin. That when you go to the magnetic state. So what we did, we have in MnBi2Te4, we have tried to dope the dysprosium, and we have seen that although this is not the scope to discuss all those things, I will go to the magnetocaloric effect, but I will just share the results and I will show the results what we observed. Actually, interestingly, we find that with the doping, that is the transition is 13K, and with the magnetic field variation, there is the change in the different magnetic state, antiferromagnetic to the canted antiferromagnetic, and then is there some ferromagnetic state. And from the resistivity data, there is a bifurcation at the different field at Tn, and that is around the 13K only. And this is the anomalous Hall effect, and also we observe the topological Hall effect here. The topological Hall effect already reported in the MnBi2Te4, but with the exposure of doping the HT phase diagram, we get that it becomes more stable slightly. However, this is under review, this paper, and this actually this is the magnetocaloric effect. You see, again we see that is at the transition temperature we are getting the maximum value, and we are getting sometimes positive slope, sometimes the negative slope. This slope again, that is due to the different state of the magnetic state, ferromagnetic, that is the antiferromagnetic, canted antiferromagnetic, ferromagnetic state, we are getting the different. So again we get from the thermodynamic, also the specific heat also give the similar kind of behavior. So again it is established that for the two-dimensional system, it is a very potential thermodynamic proof for the find the different phases. Anyway, so this is the phase diagram. Anyway, this is not for this topic. Anyway, so this is this shows that is the Lorentz space structure or topological Hall effect. That is, becomes more stable with the application of with the doping of the dysprosium. So anyway, conclusion of this talk is as we have already discussed, and finally in 2D Ising PDW materials, magnetic entropy, lattice vibration, and anisotropy exchange are strongly intertwined. So, this is the time to acknowledge they are my group. These are my two postdocs, Merus and Umashankar. They are my students. They are sitting there. And today I presented her work, and someone, she is not there. She has already joined somewhere, but postdoc Swayam Siddha. And I acknowledge the BRNS and ANRF for funding, and I also acknowledge IITB, UCIF, DACS for Indore and Kolkata Center, TI for Mumbai. Thank you very much.
Thank you, Professor Reddy, for finishing time. We can have a few questions. There has been a lot of work at IIS Bangalore, particularly by Dr. K.P. Sinha Kumar,
Okay.
on interacting spin proton systems. They have studied structure and frequency, how it modifies
Okay. Okay.
frequency magnetism and structure. So there is a book called, it was not well known, it's a beautiful book, Interacting Magnetic Systems by N. Kumar and K.P.
Okay. I'll
I
see.
encourage your students to look at that.
Okay. Thank you very
So
much.
happens K.P. Sinha Kumar would make supervisors.
Okay. Thank you very much.
So the magnetocaloric effect, how does it compare with the standard materials like gadolinium, pipe, silicon, germanium?
Oh, so that we have not done, but those materials, the magnetocaloric hot wave, that is the reported standard samples or some this kind of materials that we have matched. We measured the magnetocaloric with those materials and then we have matched that reported sample. So then if that is matching, then we have this one we measured.
Good afternoon, sir. So, may I know how does the spin lattice coupling change when we thin the material
Okay.
down to monolayer?
Yes. What is your question? Can you repeat it?
Okay. How does the spin lattice coupling change as we thin the material down to monolayer?
No, actually what is happening, I have already mentioned that is for the monolayer or what is the 2D van der Waals system, it is the strong anisotropy. Because of the strong anisotropy is the spins are oriented for the C direction and for the AB direction it is different. So that's why for the 3-dimensional system you won't get this kind of, that is the anisotropy. Generally you won't observe. In that direction it will be more helpful.
Any other question or query or comment?
Okay.
No more than thanks Professor Chakravarti for once again for finishing in time.
Okay, thank you.